ladies and gentlemen, today we introduce kind of the main event of this unit, that is stoichiometry. Again, don't let the name fool you, don't let it turn you off. Stoichiometry is the measure of amounts in a chemical reaction. And what's nice is, like I mentioned before, we're not necessarily doing anything new, we're just using it in a slightly new fashion, kind of taking it to that next step. Now, stoichiometry is incredibly powerful to us, and we've been doing this your entire life. This is how we start to look at our reaction or look at some change that's happening and start to predict how much we can get out of that. Now, again, you've been doing this your entire life. For example, if you're going to make mac and cheese and you have one box of mac and cheese, you're going to make one meal of mac and cheese. If you got two boxes, you can make 2 meals of mac and cheese, etc., etc. We can use this in cooking all the time, great analogies, but specifically, we want to look at our chemical reactions. Now, I'm going to start actually with the one from your handout, HO 9.2, just to give you an example of kind of how this starts to interplay and how we can tie it back to what we've already done. And so if you look at 9.2, our first example here is KClO3, and when that breaks apart or decomposes, it will form potassium chloride and oxygen gas. Now, the first thing you should do here, and it should scream to you, you should be like, oh, it's like nails on a chalkboard. You've got to balance it. Well, let's see. We've got one potassium, two chlorines, two oxygens, and 3 oxygen. Womp, womp. Oxygen, not balanced. Smallest number both 3 and 2 go into is 6. So we're going to need to multiply this guy by 2. That makes 6 oxygens. We'll need to multiply this by 3. But now we've got 2 potassiums. So we'll need to multiply this by 2. Gives us 2 chlorines and 2 chlorines. Now we're balanced. That's great. But what do these numbers mean? And that's really kind of the quote-unquote new piece to this unit. Let's take a look at these coefficients, these numbers out in front. Now, we've kind of seen before that these numbers will start to show us the amount of molecules in the reaction. So what this kind of implies to us is that if we had 2 molecules of this potassium chlorate, these 2 molecules will get together, they'll rearrange, they'll decompose, they'll break apart, and when they do that, they'll form 2 molecules of potassium chloride and 3 molecules of oxygen. It gives us the relative amounts that are being created or being started with, the amount we're starting with, and the relative amount that they're going to be able to make. Now, let's think about this. If 2 of these molecules will make 2 of these and 3 of these, if we had 4 of these molecules, well, really that would mean we can make 4 of these and 6 of these. And so these coefficients tell us the relative amounts needed for a reaction. We need, in generality, for every 2 of these, we can make 2 of these and make 3 of these. If we started with 4, we can make 4 of these and 6 of these. Well, we can use whatever number we want in this reaction. Well, let's say you started with 6.02 times 10 to the 23rd of these, which makes sense. Molecules are pretty little. We need a lot of them to make the reaction visible to our kind of pale or weak human eye. Can't see very small. So if we had a whole bunch of these, and, well, we said for every 2 of these, we make 2 of these. So if we had this many molecules of potassium chloride, we would make, well, 6.02 times 10 to the 23rd of these. Now that is just kind of cumbersome. That's a lot to write. And we actually know that 6.02 times 10 to the 23rd is something else. It is a mole. So for example, if we had 1 mole of this potassium chloride, we have 1 mole of potassium chloride created. And here is the gap where we can go from moles, from what we can measure in lab, because you know that we can go very easily from grams to moles. And we now can go from moles of one substance to moles of another using these coefficients. And this gives us a new tool. We call it the mole ratio. The mole ratio. And the mole ratio comes from the coefficients in your balanced equation. We already know how to find coefficients. We just balance our equation. All we're going to do now is start to look at them as a new tool. It makes a bridging gap. Now, a real nice infographic, a real nice way that we can start to think about this. I'm going to use kind of some generalities, but I want to get this to you today so you've got this for your notes. If you were given some grams of a substance, for example, grams of substance A, whatever it might be, it can be any substance we want. If you were given grams of some substance, we know that we can change those grams into moles. And again, this would be moles of substance A. Now, what's nice, you're starting to think, ooh, this is mole train. But we're going to change it just a little bit because now we know that atoms can undergo changes, rearrange, and react to form new substances. So we can go from grams of A to moles of A. Well, we would use the molar mass of A. Cool. That's nothing new. We've been doing molar mass since Unit 2. Long time. Been smoking this. You guys got this. Got it hands down. The new piece is we now have a way to go from moles of some substance to moles of a different substance. And to do that, we use what is called the mole ratio. And don't let that frighten you. The mole ratio is just the amount, the coefficient in front of your substances in your balanced equation. What's nice, however, is that the mole ratio will allow us to go from moles of some substance to moles of a different substance. I'm going to just call it generic moles of B. Moles of something else. And we can solve whatever something else we might want, whatever the question might ask. We can use this kind of moles A to moles B mole ratio to solve whatever we might need to. Cool. Now, if we really needed to, and if we were interested, if, for example, we were working in the lab, we don't measure moles of substances, we measure grams. Well, if we want to, we can go from moles of B back to grams of B using the molar mass of substance B. Again, B just being a generic substance that we're solving for, that we're interested in. Well, cool. Molar mass, that's not new. Molar mass, that's not new. The only thing that's technically new is the mole ratio, but that's just the numbers coming from your from your balanced chemical equation. Well, I said let's look at some from the homework. Let me help you kind of set up a couple of these just to kind of be thinking about them, just that you've got some examples to go back and look at. I'll leave this kind of altered or kind of transitioned mole train up here so that we can kind of reference it as we go. If we look at number 1, we've got in a decomposition of potassium chloride, how many moles of potassium chloride can be made from 34.0 moles, 34.0 moles of potassium chlorate. Well, that sounds like the given. And we're trying to figure out how many moles, question mark moles, potassium chloride. Well, the good news is we have an equality statement to do this. If we look at our mole train, we're starting in moles of some substance, in this case, moles of this potassium chloride, and we want to get to moles of substance B. Oh, that's nice. It's a one-stepper. That's awesome. Now, we already saw that for every 2 moles of potassium chloride, we will create 2 moles of potassium chloride. Well, wait a minute. So based on our balanced chemical equation, based upon the law of conservation of mass, you just told me that 2 moles of potassium chlorate will equal 2 moles of potassium chloride. Wait a minute. Equality statement, conversion factor. All we got to do is use this to change our moles. Now, you'll notice I'm writing the moles down. I'm writing what the moles of stuff are so that we can keep track where we're at in our ratio. So our technically new step, our bridge from here to here is that mole ratio. Now, we're starting with moles, potassium chloride on top. And our equality statement says that for every 2 moles of that, we get 2 moles of potassium chloride. Well, if we use this equality statement as a conversion factor, for every 2 moles of potassium chlorate, we will create 2 moles of potassium chloride. Well, cool. If we look at our units, they're kind of weird, but they tell us, they give us our units we're looking for. The moles of potassium chlorate cancel, and we're left with moles of potassium chloride. Again, dimensional analysis, we've been doing this all sorts of times. Well, to solve that, we're going to take 34 times 2, divided by 2. Well, 2 divided by 2, for all you math studs out there, is the same amount. Now, this kind of makes sense. We said that for however much of this you start with, you're going to make the same amount of moles here. Well, if we start with 34 moles, we're going to end with 34 moles. But it's still a nice way to kind of see this mole ratio in action. How we can make this equality statement and use these coefficients in our mole ratio. Now you might be asking yourself, well, why do we have to go from grams to moles? Why can't we just go from grams, mole ratio to grams? Well, think about it this way. If you've got 12 preschoolers and 12 high schoolers, you have the same amount of both of them, but their masses are considerably different. Potassium chlorate has a larger mass than potassium chloride. We can't compare the masses directly, just like we couldn't compare them earlier directly. We have to get rid of the mass and get into moles before we can start to do our mole ratio. Let's take a look at the second problem here. It's a little bit different, a little bit more involved. Second question. Oh, but that's nice. It uses the same reaction. So I'm going to go ahead and leave it up here. I'm not going to reinvent the wheel. We're going to have the same reaction, but this time, ooh, there's 2 question marks. Oh, cool. So first question mark, how many moles of potassium chloride are required or are needed to produce 2.3 kilograms of potassium chloride? Ooh, okay. We're starting in kilograms, and we want to know how many moles of potassium chlorate are required. What's nice is our recipe kind of works both ways. If I told you you had you made 2 dozen cookies, you could work back from the recipe to say, oh, I started with 4 eggs, right? You could also say, I had 4 eggs, I made 2 dozen cookies, I got 2 dozen cookies, I must have started with 4 eggs. But the proportion, the ratio, works both ways, just like we've seen with molar mass. We can go from grams to moles, or moles back to grams. Well, we're starting in kilograms. King Henry died by drinking chocolate milk. So you could go ahead and slide your decimal around. You could also say, well, 1 kilogram is bigger, and in 1 kilogram, King Henry died by drinking chocolate milk. We slide over 3 spots. There are 1,000 grams for every kilogram. Kilograms cancel, gives us into grams. Oh, now we're on the train. We're in grams of A. But we are trying to get, now grams of A, again, just being any substance, we're in grams of some stuff now. But we want to get into moles of some other stuff. In this case, potassium chlorate, KClO3. Well, if I look, I've got 2 arrows. If it helps you, put your 2 lines. You know this is going to have 2 more conversion steps to get you where you're trying to get to. Well, we're here, grams of a substance. Our next step is going to be to find the molar mass of potassium chloride. Well, okay, we look at potassium chloride. Potassium, 20, excuse me, sorry, I don't have that number right off the top of my head. Potassium, sorry, 39.10. Mass of potassium. Chlorine, 35.45. We add those together. 5, 4, 6, 74.55 grams per mole. Cool. Awesome. Well, we're in grams on top. We're going to put our 74.55 grams on bottom. And that is equal to, our molar mass is equal to 1 mole of A, of the original substance. It's still changing us into moles of that original stuff. So we're still now in moles of potassium chloride. Oh, we're so close. We're in moles of one thing, we need moles of something else. We're going to use our mole ratio. And hey, lo and behold, it's the same ratio that we used before. We're just going to flip it. This time, we're going to put our 2 moles of potassium chlorate on bottom. Sorry, excuse me, potassium chloride on bottom for every 2 moles of potassium chlorate. We check our units here. Kilograms we already canceled. Grams we cancel. Moles of potassium chloride cancel. And we're now in moles of potassium chlorate. We now have a way to figure out, based on the amount of stuff we got, how much reactant we must have started with. Because we have the recipe. We have the balanced equation. We know how much it takes to make this reaction go. Right. I'm going to leave it to solve for you guys. You've got your calculators. Looks like we've got 2 sig figs here. Going to need 2 sig figs in our answer. Make sure you're watching your precision as you're working through these problems. I will leave the rest of these to you guys. If you have questions, feel free to email. Give it your best shot. I do anticipate that there will probably be some questions when we get back together tomorrow. That's going to be okay. I wanted to get you started with this, to get you thinking about it, get you this awesome tool to kind of help you navigate these problems. Give it your best shot. Do the best you can. We'll see you guys back here next time.